We've learned to take the derivative and integrate several different types of functions, but we're going to learn about another set of functions called natural log and logarithmic functions that we'll be able to work with as well. So to get started, let's go ahead and look at these functions and some of their characteristics. Let's go with the natural log function to start with. So let's go ahead and look at the natural log of the value of x, natural log of x. Always put parentheses around the arguments of your trig functions and your log functions. That way, if we have something like a plus 3 off to the side, we know that it's not the natural log of x plus 3. So we need to make sure that we kind of can clarify that by always putting parentheses around the arguments of your log function. So first of all, let's go ahead and look at a quick graph of a log function. When we're talking about a log function, and you probably have an ln key on your calculators if you want to check through any of these values, there's some very specific kind of hinge points that we look at that allow us to determine some of the characteristics of a log function. So on your calculators you'd use ln. ln stands for natural log. So this is the natural log. And the reason it's called the natural log is it has a log base e, which is e the natural number. So this is log base e of x. So e is a natural number, so that's why this is called the natural log. Okay, let's go ahead and pop this into our calculator. Whoops. So some typical values that we might want to look at. The ln key on your calculator is usually located right around somewhere with a log key. So here's our log key, here's our ln key. Let's go ahead and take the ln of a very small number, let's say like 1/2. And again, I want to make sure that I have parentheses around the arguments of my log function. You can see that the ln of 1/2 is a negative number. Let's keep looking at that. Let's do the ln of 1/100th. Well, that's a really big negative number, and as we go 1/1000th, 1/10,000th, etc., this is going to get to be a larger and larger negative number. Let's go ahead and look and see what happens if we take the log of 0. The log of 0 says we have a domain error, which basically means the log of 0 is undefined. Let's look at the log of 1. This is an important point to make sure you have memorized. The log of 1 is 0. Okay, so that's going to be an important point on our graph. And now let's also look at one other one. Let's look at the natural log of e. And I'll just look at the natural log of e, and we can see that we get 1 out of that. So those are some important hinge points that we'll want to keep our eye on for our graph. So let's go ahead and look at that first one that we had that was interesting, 1. The natural log of 1 is 0. So this is this important point that it goes through. Also, the natural log of e is approximately 2.72. This is a non-terminating, non-repeating decimal like pi. It's a rational number, so that's why this is only an approximation. So e is somewhere, let's say here's 1, 2, 3. E would be somewhere right about here. The natural log of e is 1. Now for everything between 0 and 1, these are those very large negative numbers. And this will continue to grow very slowly. So this is the general shape of our natural log graph. Now let's talk about its domain. I can't take the log of a negative number. If you want to plug some values into your calculator to determine that, you can. So the domain is 0 to infinity, not including 0 or infinity, because this is a vertical asymptote. I get closer and closer to 0 but never actually equals 0. And my range is all real numbers from negative to positive infinity. Now it's going toward positive infinity very, very slow, but it is heading off in that direction toward my y value, toward positive infinity. So that's the domain and the range of the natural log function. Now we have a specific derivative and integral that we work with in terms of the natural log function. But before we get into those derivatives and integrals, we want to look at a few other properties of logs. A couple important logs that we should always remember are the natural log of 1 is 0, and the natural log of e is 1. So these are some important points to remember. Also, the natural log of 0 is undefined. It does not exist. And I cannot take the log of a natural number. and not just the natural log, but any log of a negative number. Okay, so keeping those things in mind, let's go ahead and look at some properties of logs. These are probably going to be a bit of a review for you from your algebra course, but let's go ahead and look at these anyway. And these are not only just for ln's, these are for any logs, but we'll just, since we're just working with natural logs right now, we'll look at these as properties of natural logs. So we've already talked about the domain and the range. Let's talk about the log of a product. The log of a product is the sum of the logs. So this would be the natural log of x plus the natural log of y. I can rewrite this expression, the log of a product is the sum of the logs. And again, always put parentheses around the arguments of your log functions. I can also look at this for the quotient. The log of a quotient is the difference of the logs. Natural log of x minus natural log of y. I can also look at the log of x to the p, let's say. I also have the log of x to some power. And if I wanted to rewrite this, this could also be x to the p. It's the argument that's raised to the power, not the log. What I can do with this is I can pull that exponent out front. So that's another interesting property of a log. Now let's go ahead and get into our derivatives a bit. Now all of these are defined only when x or y is greater than 0. So we have to keep that in mind. If we're looking at these values, they have to follow the domain up here. So properties of logs. Let's look at the derivative with respect to x of the natural log of the absolute value of x. Now another way we could write this is a derivative with respect to x of the natural log of x given that x is greater than 0. So if you have the absolute value, what they're saying there is only consider positive x, and this means the same thing. Well, the derivative of the natural log of x is 1 over x times the derivative of x, which is 1. So the derivative is just 1 over x. And of course this will be true for values of x that cannot equal 0. Now this has to be true for values of x that cannot equal 0 because I can't have a 0 in the denominator. Now let's go ahead and look at what if the log argument was not just a straightforward nice little x, but what if it was an entire algebraic expression? So let's go ahead and look at the natural log of the absolute value of some function of x. So I'm going to call it u of x. Well, this is equal to 1 over u of x times the derivative of u of x. So the way I always remember this is 1 over u prime. Now a lot of times you'll see this written as a single fraction. If you don't like the 1 over u prime, you can just write it as u prime over u. Now u is an entire algebraic expression, and we'll look at lots of examples here. Now the next one we want to look at is the integral. Now we're not integrating the log. We can't do that until Calc 2. We don't quite have the tools in place for that. But what I can integrate is the integral of 1 over x dx is equal to the natural log absolute value of x plus c, my constant of integration. Now let's go ahead and check this off to the side. We can check this by taking the derivative of the natural log of x, and again I get 1 over x times the derivative of x, which is 1. So this checks. I get my integrand back. So these are the important things that we need to know about logs. Let's go ahead and run through quite a few examples of taking derivatives of logs. Let's look at the derivative with respect to x of the natural log. Let's do 10x cubed plus 7x. Now what we're going to assume here is the log argument is going to be positive. I'm only using values of x that would create a positive argument here. So the derivative of the natural log of u is 1 over u, which is the argument, times the derivative of the argument. So I'll write out my steps here. So the derivative again is 1 over u, 1 over my argument, times the derivative of my argument, which is 30x squared plus 7. So I can rewrite this as 30x squared plus 7 over 10x cubed plus 7x. So that's my derivative. Now remember, this derivative still has the same meaning as it always has. It's the slope of the tangent line at any point along the curve. It's also the rate of change. So even though we have a new function we're working with, the idea of the derivative is still identical. Let's look at the derivative with respect to x of the natural log of the absolute value of sine of x. Now the reason that we have the absolute value here is, remember, sine goes from -1 to +1. So this is saying no matter what value you get, positive or negative, we can only look at the positive because I can only take the log of a positive number. I can't take the log of 0 either. Okay, so I have to be careful about things like the sine of 0 or the sine of pi or the sine of 2 pi. So the derivative of the natural log of an argument is 1 over your argument, so 1 over sine of x, times the derivative with respect to x of the sine of x. And of course the derivative of sine is cosine. And cosine, I could write this as cosine of x over sine of x. Cosine over sine is the same as cotangent. So I could simplify it completely down to cotangent. So again, 1 over u prime. We can also get into product, quotient, chain rules with derivatives. So let's look at the derivative of the natural log, and my argument here will be a quotient. So 2x plus 1 over 2x minus 1. Now I have two options here. Option 1, use the quotient rule. And if I do that, my derivative, and I'm just going to call it y prime, would be 1 over my argument, 2x plus 1 over 2x minus 1, times the derivative of the argument. So then I'd have the derivative of 2x plus 1 over 2x minus 1. So y prime would equal, when you divide by a fraction, you multiply by the reciprocal, so this flips. And then the derivative here would be the bottom. Back to the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so simplification here is definitely going to be an issue. 2x minus 1 cancels with one of these on the bottom. And let's see what we have for simplification. So I have y prime equals 2 distributed would be 4x minus 2 minus 4x minus 2 all over 2x plus 1 times 2x minus 1. And of course this is going to simplify a little bit more. We can combine like terms and end up with y prime equals the 4x and the negative 4x cancel, and I'm left with negative 2 times negative 2. I'm sorry, minus 2 minus 2, not multiplication, which would be a positive 4 over 2x plus 1, 2x minus 1. So that would be option 1. Let's go ahead and look at the same derivative, option 2. Option 2 is I can rewrite using our properties of logs. So I'm looking at the derivative with respect to x of the natural log of 2x plus 1 over 2x minus 1. Well, I can rewrite that. The log of a quotient is the difference of the logs. So this would be the derivative with respect to x of the natural log of 2x plus 1 minus the natural log of the argument 2x minus 1. And again, please always put parentheses around the arguments of your log function. If you don't, it's confusing. Do you mean 2x for the argument or 2x plus 1? So always be clear on that. So my derivative, I'm going to call that y prime for my first one, would be 1 over u times the derivative of u. And the derivative of 2x is 2. Minus 1 over u times the derivative of 2x minus 1 is 2. So if I find a common denominator here, I have 2 times 2x minus 1 minus 2 times 2x plus 1 over the product 2x plus 1, 2x minus 1. So distributing, I get 4x minus 2 minus 4x minus 2. This is starting to look familiar, times 2x plus 1, 2x minus 1. And the 4x's cancel. Negative 2 minus 2 would be a negative 4 over 2x plus 1, 2x minus 1. So we get the same answer either way. So it's totally up to you what you decide to do. Well, wait, we didn't get the same answer. The top one's positive. Ah, I just forgot to bring the negative along. Negative 2 minus 2 is a minus 4. So we get the same answer either way. The important part is that you show your work to justify your solution. And as usual, you're judged based on your work and how you communicate how you do your math. You're not just judged on the solution. So you can use the quotient rule or you can rewrite. And I think the rewrite's a little easier here, but again, it's your choice. Let's look at a problem where we're talking about the derivative of the natural log, but we end up using the quotient rule. So let's do x squared plus 6 times the ln of x. So this is a product rule. Here's my first function. Here's my second function. So my y prime, if you remember the product rule, would be the first times the derivative of the second plus the second times the derivative of the first. So this simplifies a little bit, not a lot. This is not going to look as nice as our quotient that we had up here. This would be x squared plus 6 over x. And I'm going to pull this 2x out front here just so I don't get it confused with the log. Now if you wanted to rewrite this as a single fraction, you could. This would be x squared plus 6 plus 2x squared ln of x all over x. Now none of these terms combine. I can't combine the x squared because they're combined with the logs. Now how did we get to this point? Remember, this is over 1, and then I could multiply top and bottom by x to get that common denominator. So sometimes when you're working with these, you're not going to get a real nice expression, but it has the same meaning. It's the slope of the tangent line at any point along the curve. A couple of nice derivatives to end up with here. The derivative with respect to x of the natural log of 4x is 1 over 4x times the derivative of 4x, which is 4. And of course the 4's cancel here, and I'm just left again with 1 over x. So this is one that comes up quite a bit. Now when we're looking at derivatives, we can also start thinking about antiderivatives. So antiderivatives, let's look at the integral of 1 over, let's say, x plus 4. So what we do here, and remember what we figured out before is what was given with our properties of logs. We want to use the fact that the integral of 1 over x dx is equal to natural log absolute value of x plus c. But if I could rewrite this as a 1 over u du, that's natural log absolute value of u plus c, where u is any function of x. So this could be 1 over x plus 4, for instance. So what we do is we let u equal x plus 4, and then we take its derivative, and we use a u substitution here. So let's let u equal x plus 4, du is equal to dx, and then I rewrite. So 1 over x plus 4 is 1 over u, dx is du, and the integral of 1 over u du is natural log absolute value of u. Then we convert it back to x. My original was in terms of x, and so should my solution be. U is equal to x plus 4 plus c, my constant of integration. Okay, so this is an example of using that integral to help us figure out what integrates to the natural log by using u substitution. Let's look at another example. Let's look at something like x over x squared plus 4 dx. So this looks like I could use a u substitution here. I can't split the denominator up. I could split up the numerator, but it's only a single term. So u is equal to x squared plus 4. du is 2x dx. Now if you look at this, I have the x, which is good because I need the x. I'm missing the 2. So I'm going to multiply by a 2 on the inside, and then I'll compensate with a 1/2 on the outside. So this bit right here becomes my du. This bit right here becomes my 1 over u. So this is 1/2 the integral of 1 over u du, which is 1/2 natural log absolute value of u But u, I need to convert back, is x squared plus 4 plus c. You need to have that absolute value. Something to think about though, if I take any value of x and squared, it's going to become positive. Positive plus 4 is still positive. So I guess you could drop the absolute value, but it works well for a grouping symbol, and it's nice to stay in the habit. Let's go ahead and look at a definite integral this time. Let's look at the integral from 0 to 8 of 2x minus 4 over x plus 1. Now, we haven't ever done this before, but we could use synthetic division to simplify this, or even I like long polynomial division, but that's usually a technique that we get into a bit in Calc 2, but if you've seen that before, that would be a nice way to simplify this. We can't use a 1 over u du here because I'm going to be left over with a variable. So there's several different ways I could work this problem. I think let's go with a straightforward u substitution. So let's go u equal the denominator, x plus 1. And the reason I'm going to choose the denominator is that I want to get this into a form like 1 over u du. So of course du would be dx. And when I start doing my sub in, then x plus 1 is u, du is dx. And then if you look at this, I'm left over with 2x minus 4. This is not good. So I need to come over here and I need to solve x is equal to u minus 1. This is change of variable. So this is 2u minus 1 minus 4. I'm going to make some more room here. Plus that du should have been, or that dx should have been a big du. So 2u minus 1 minus 4 all over u du. Now notice I dropped my limits of integration. If I wanted to, I could convert my limits of integration. Remember, my upper limit is x equal 8 and my lower limit is x equals 0. This would imply that u would equal to 8 plus 1 is 9. This would imply that u is equal to 0 plus 1 is 1. So I'm going to write these in as u so I don't forget that I don't have to convert back if I don't want to. In fact, I shouldn't convert back after I change my limits of integration. Okay, so we're going to simplify this. So again, I'm going to keep my limits of integration. So I have 2u minus 2, which would be minus 2 minus 4 is minus 6 all over u du. Okay, I'm going to keep rewriting this. U equal 1 to u equal 9. So I have 2u over u, 2u over u, minus 6 over u. Okay, we're simplifying. U equal 1 to 9. 2u over u simplifies to 2. So what I have here is the integral of 2 is 2u. The integral of minus 6 over u is minus 6 natural log absolute value of u. Now again, I don't have to convert this back to x because I already changed my limits of integration. So 2u minus 6 natural log absolute value of u evaluated from u equal 1 to u equal 9. So as usual, when we put up our evaluation, we need to put up our brackets to make sure the negative sign distributes correctly. So I'm going to put in the 9 first. So I have 2 times 9 minus 6 natural log absolute value of 9. And I know that the absolute value of 9 is 9, so I don't necessarily need the absolute values there, but it's a good grouping symbol. But if you want to drop that and put that in parentheses, that's fine too, which we'll probably do in the next step. Minus the lower, make sure you have these brackets up. So I have 2 times 1 minus 6 natural log absolute value of 1. So rewriting, I have 2 times 9 is 18 minus 6 natural log of 9 minus 2 minus a negative is the same as a positive 6 natural log of 1. Now if you recall, one of the interesting characteristics about the log is the natural log of 1 is 0. 0 times 6 is 6. So here I have 18 minus 2 is 16 minus 6. I can rewrite this though as natural log of 3 squared. So I want to be able to simplify these as much as possible. Now remember, properties of logs, I can pop this 2 out front. So this would equal to 16 minus 6 times 2 is 12, natural log of 3. So this would be simplified completely. I can't break this down any further. I can't combine the 16 minus 12 because the 12 is being multiplied by natural log of 3. So that's my solution. That's my equivalent. Now again, you can check a lot of these on your calculator while you're working on your homework or your handwritten homework. But remember, you have to be able to show your work. Without being able to show your work and communicate your steps in your mathematics, there's not a lot of credit involved for that type of solution. So that's a quick overview of the natural log function and its derivatives and how we can look to integrate a function to get the natural log. Now what I want to look at is the exponential function. Now this particular exponential function that I'm going to be looking at has a log base e. Okay, so exponential function in particular that I'm going to be looking at has that log base e. Now the reason we're looking at this now is it is the inverse function of the log. Okay, so exponential function that we're looking at is y equal e to the x. So let's go ahead and graph this. We already know what our log graph looks like. Our log graph has this really important hinge point right here at 1, 0. Now, e to the x, this is ln of x right here. E to the x has a very important characteristic. It's the inverse of the natural log. So an inverse reflects over this line y equal x. So this is the line y equal x. So y equal e to the x is the inverse of y equals ln of x. Now these variables are going to get a little dicey because they're because their inverse is the x and the y swap. But let's go ahead and just look at the graph. Now this is the ordered pair 1, 0. Now remember, one of the characteristics of an inverse is the domain and the range swap. So over here I would be looking at the point 0, 1. These points down here that are going toward negative infinity would start moving up here as it reflects across this y equal x line. So this is a graph of y equal e to the x. Now let's talk about its domain and its range and some other interesting characteristics. So its domain is all real numbers. That comes from the range of the log. Its range goes from 0 to infinity, parentheses on either end because I cannot equal 0 and I cannot equal infinity because this is a horizontal asymptote here. So if you notice, these are just swapped from the domain and the range of the log function. Let's go look at some other important characteristics. E to the 0 is 1. Anything to the 0 power is 1. That's this point right here. E to the first is e. I guess that's not all that interesting. What are some other ones? We could look at e to the negative 1. That's 1 over e. So that would be somewhere down in here. E to the negative 1 is 1 over e. It's a fraction of about a third or so. So those are some interesting characteristics of our exponential graph. Now we also, just like we had characteristics or properties of logs, we also have properties of exponents. Now these are a review, so these are probably pretty familiar to you, but we want to make sure that we rewrite these so you have them to work with as well. So properties of e to the x. So one of the first properties is e to the x times e to the y. When you multiply like bases, you add exponents. When you divide like bases, you subtract exponents. When you raise a power to a power, you multiply the powers. And then we could also look at something like when you raise something to a negative exponent, e to the negative 1, that would equal 1 over e. We would flip that. We could also look at the natural log of e to the x. That's going to be interesting. Remember, we can pop that exponent out front, and I'm left with equals x natural log of e, but the natural log of e is 1, so this just equals x when I simplify it. And we can also do a conversion back and forth from log to e to the x, power of e to the x, the exponential. And we can also rewrite e to the ln of x, this is in the exponent, is just another way to rewrite x. Now the way we can get this figured out is if we took the ln of both sides, I could pop the ln of x out front, and then the ln of e is 1, and then the arguments have to equate. So that's another thing that we can look at, and of course all of this hinges on the fact that the argument of the log has to be greater than 0. So of course this value also has to be greater than 0, so keep those in mind. Now let's go ahead and look at writing things kind of flipping around back and forth. If I have an exponential expression like y equal e to the x, I can rewrite this as log base e, because natural log is log base e, and e is my base, so log base e of y equal x. Now this can be rewritten, log base e is the same as the natural log of y equal x then. Now notice this is my base, this is my exponent is on the right hand side. You can also think of this as like a counterclockwise circle. My base is e to the x equal y. A lot of people try and put this y as the exponent, but just remember it's not your exponent, it's your solution if you want to think about that over here. So all of these are some interesting properties of logs. Some other important characteristics of logs that we're going to be looking at are derivatives. So let's go ahead and look at the derivative of e to the x. The derivative of e to the x is nice because it's just e to the x. So the derivative of e to the x, let me rewrite that a little bit better. The derivative of e to the x is e to the x. Now what if the exponent was not just an x? What if it was a function like u? So the derivative of e to the u is e to the u times the derivative of u. So the way I kind of shorthand this is I say, oh, that's e to the u, u prime. So the derivative of e to the u is e to the u, u prime. Now we haven't talked much about integrals yet, but the integral of e to the x dx is just e to the x plus c. This checks because the derivative of e to the x is e to the x. So we haven't really gotten into anything where we have an argument more complicated than x right here for our exponential function, but we will. And it won't be any more complicated than replacing their x's with the u's. So the integral of e to the u du, we have to make sure we have a du there, is e to the u plus c. So let's go ahead and try some of these derivatives and integrals. And again, I can combine these with product quotient chain rules and they get pretty interesting. But I need to remember the base derivatives and the base integrals to get started. So let's go ahead and look at, let's do an interesting one right away. Let's do a quotient rule. Let's look at f of x equal 4 e to the x minus 4 over 4 e to the x plus 4. So this is a quotient rule. So f of x equals this function. F prime of x would be the quotient rule. So I'd have the bottom times the derivative of the top. And I'm going to write out these steps for this one because we haven't done any derivatives with these functions yet. So the bottom times the derivative of the top minus the top times the derivative of the bottom and this is all over the bottom squared. Okay, so we haven't taken our derivative and we also need to simplify, so we have quite a bit of work left to do here. So I have 4 e to the x plus 4. The derivative of 4 e to the x is just going to be 4 e to the x, because remember the derivative of e to the x is e to the x, and I just drag along the 4. The derivative of a negative 4, derivative of a constant is 0, minus 4 e to the x minus 4. And then again, the derivative of 4e to the x is 4e to the x, and the derivative of 4 is 0. And this is all over 4e to the x plus 4 quantity squared. Now we need to simplify this. If I want to, when I'm looking at this numerator, I see that there's a 4e to the x that's common here. So if I pull out a 4e to the x for both of these, I'm left with 4e to the x plus 4 minus 4e to the x plus 4. So I'm taking this negative and I'm distributing it through here. So minus 4e to the x plus 4. And this is all over 4e to the x plus 4 quantity squared. So simplifying inside my brackets here, the 4e to the x cancel, and I'm left with 4 plus 4 is 8. And of course I'm going to be able to simplify this a bit. This is all over 4 e to the x plus 4 quantity squared. 8 times 4 is 32 e to the x all over 4 e to the x plus 4 quantity squared. Now remember, this is our definition slope of the tangent line at any point along the curve. So if I was given an ordered pair, I would be able to find the equation of the tangent line. So the derivative of e to the x is e to the x. Let's go and look at another problem. Here we have f of x. This almost looks like a polynomial expression, but it isn't. Negative 4 e to the negative 3x minus 3e to the 3x minus 5e to the x. So notice my arguments are changing here. Here my exponent is a negative 3x. So my derivative, I don't have a product rule here because this is just a constant, so I can drag it along. The derivative of e to the u is e to the u times the derivative of u, which in this case is the derivative of negative 3x. Okay, the derivative of e to the 3x is e to the 3x times the derivative of 3x. And the derivative of e to the x is e to the x times the derivative of x, which is just 1. Now of course we'd want to simplify this. So I have negative 4 times negative 3 is 12e to the negative 3x. Here I'd have a minus 9e to the positive 3x minus 5e to the x. Now I notice I have an e to the power everywhere along here, and I'm kind of tempted to factor it out. I could pull out an e to the negative 3x and work with this, and this would end up being like e to the 6x and e to the 4x, but I think that's not really going to do us any good. There's no benefit to it in terms of simplifying, so I'm just going to leave this one as is. Now we could also have trig involved in these, and of course anytime we can have trig involved in calculus, that's always a good thing. So let's look at an example where we have f of x equals, let's do 2 tangent 3 e to the 4x. Okay, now derivative. This is not a product rule because this is not a function. This is just a constant, so I just drag it along. The derivative of tangent u is secant squared of u times the derivative of u. Okay, so the derivative of u, and please always put parentheses around the arguments of your trig functions just so you can distinguish between what's argument and what's coefficient. The derivative of 3e to the 4x is 3e to the 4x times the derivative of 4x, which is 4. So simplifying, it looks like I have a 2, 3, 6 times 4 is 24, e to the 4x out front. And I'm pulling everything out front that I can so I don't get anything confused with my trig function. And there's my derivative. Just a quick little simplification there. Now, we can also look at an expression, like I said, given an ordered pair, find the equation of a tangent line, or evaluate at a particular point. So let's look at an example where we're given a function f of x equals the natural log of e to the 3x plus 2. Now, the plus 2 is not in the exponent, but what I'm not clear about here is our parentheses. Is just this, Is this just the natural log of e to the 3x, or is it e to the 3x plus 2? So we have to be pretty clear about these when you write them out. So let's go ahead and jump back a little bit. Our derivative then would be, derivative of the natural log of u is 1 over u times the derivative of u. And the derivative of u is e to the 3x times 3. So simplifying, I have f prime of x equals 3e to the 3x over e to the 3x plus 2. So there's my derivative. This is kind of an interesting little problem. And what I could do then is I could evaluate these at different points. I could be given an ordered pair and asked to find equations of a tangent line. So if we were just asked to find the derivative, we could stop right here. But what if we were asked to evaluate, let's say at x equals 0. So if we evaluated this at x equals 0, that would be f of 0 would be 3e to the 3 times 0 over e to the 3 times 0 plus 2. E to the 0 is 1. 1 times 3 is 3. 3 times 0 is 0. E to the 0 is 1. 1 plus 2 is 3. So 3 over 3 is 1. So this would be the slope of the tangent line when x is equal to 1. Now you could also come back here and find the y value by plugging in. E to the 0 is 1. 1 plus 2 is 3. So the y value would be the natural log of 3. So you could actually write an equation of the tangent line as well. Let's look at another one. Let's evaluate at x equal, let's do something interesting here, the natural log of 4. So this is going to be f prime of the natural log of 4. This is equal to 3e to the 3 times the natural log of 4 all over e to the 3 times the natural log of 4. I'm going to need one more parentheses there, plus 2. So this has quite a bit of simplifying to do. I could rewrite this. This is 3e to the natural log of 4 cubed, because this 3 I can pop up into the exponent, and I can do the same thing down here. E to the natural log of 4 cubed plus 2. Now notice the plus 2 is not in the exponent, it is down in the base. And it's not the base of the exponent, it's the base of my next term. So to finish simplifying this, we need to recall one of our properties, and that was e to the ln of x. I can rewrite as just x. Remember, this is log base e, so if you want to think about these as canceling, you could. So when I rewrite up here, I end up with these e's, this e to the natural log, or e to the log base e of 4 cubed, just simplifies to 4 cubed. In the denominator, this just simplifies to 4 cubed as well, plus 2. So multiplying 4 cubed is 64. 64 times 3 would be 64 times 3, 192. 4 cubed is 64 plus 2 is 66, and of course I'd want to reduce these. These are both even, so I could reduce them by a factor of 2, so 96 over 33. Both of these are divisible by 3, so that reduced to 32/11. Okay, so just an example, another type of problem you can use. This is the slope of the tangent line at x equal natural log of 4. So those are some examples of some derivatives. Did we ever do a trig derivative with an e? I don't think we did. So let's do a trig derivative with an e. Let's look at, let's even evaluate it. We can write an equation of a tangent line, maybe even. That would be exciting. Let's look at the derivative with respect to x of e to the cosine. Let's do tangent. Tangents are fun. E to the tangent of pi x evaluated at x equal 1/2. Okay, so let's go and take our derivative. The derivative of e to the u is e to the u times the derivative of u. This would be the tangent of pi x. Okay, so this would be the derivative of e to the tangent of pi x. And then the derivative of tangent pi x, derivative of tangent is secant squared pi x times the derivative of pi x. Okay, so I'm taking that chain rule as coming into play here. So this would equal e to the tangent pi x, doing one chain piece at a time, secant squared of pi x, and the derivative of pi x is pi. So now I want to evaluate this at x equal 1/2. So this equals e to the tangent. I'm plugging in a half here, so that would be pi over 2 times the secant squared of pi over 2 times pi. And I think we're going to run into some problems here. That's what happens when you make up problems on the fly. The tangent of pi over 2, tangent is sine over cosine, and this is where I run into my problem. Tangent of pi over 2 then would be sine of pi over 2 over cosine pi over 2, which is 1 over 0, so it's undefined. So I'm going to change my value. Let's change it to 0. And the reason I'm changing this is not possible. I can't evaluate this. These are undefined values. So this would change it to the tangent of 0, and this would be the secant squared of 0. So the tangent of 0, that would be sine over cosine. Sine of 0 is 0. Cosine of 0 is 1. So this is just e to the 0. Now secant squared of 0, that's 1 over cosine squared of 0 times pi. E to the 0 is 1. Cosine of 0 is 1. 1 squared is 1. 1 over 1 is 1 times pi. And I get pi for my solution here. So that's an example of finding the slope of the tangent line at this particular function at x equals 0. So working with trig functions is neat. Now we haven't done much with integrals of e to the x other than just looking at that basic formula. So let's go ahead and look at some integrals of e to the x. So this would be, let's look at the integral of e to the 5x dx. Well, I'd use a u substitution here. So I'd let u equal 5x. du would be 5 dx then. I'm missing the 5, so I'm going to multiply by a 5 on the inside, compensate with a 1/5 on the outside, and I'm left with 1/5 integral e to the u, and then 5 dx becomes my du. And of course the integral of e to the u is e to the u. Have to convert back to x. 5x is equal to u, so this is 1/5 e to the 5x plus c. And you can check this solution by taking the derivative of your solution, and it should equal the integrand right back. Let's go ahead and look at another one. Let's look at the integral of e to the negative x dx. Same approach. I need to have a u. U is equal to a negative x. Du is equal to a negative dx. So I multiply by a negative on the inside, compensate with a negative on the outside, and I have negative integral e to the u du. Dragging along the negative, the integral of e to the u is e to the u. Converting back, I get e to the negative x with the negative out front plus c. We don't usually like to leave things with negative exponents, so this is negative 1 over e to the x plus c. And you always just have to kind of look at the context of the problem or your instructions, where it might say something like don't leave negative exponents. I want to give you a few more examples of these. So this will kind of add some length to the lecture, but I think it'll be nice to have a few more examples. Let's look at the integral of, let's say, 1 plus e to the x over e to the x dx. I can separate the numerator. I can never separate the denominator, but I can separate the numerator. So this is going to be 1 over e to the x plus e to the x over e to the x. Rewriting, I'd flip that e to the x up top by negating the exponent. E to the x over e to the x is 1. And then I have for my result right up here, e to the negative x, I'd let u equal negative x. Du is negative dx. So I multiply by a negative on the inside, compensate with a negative on the outside. And then I'm going to split up my second integral as 1 dx. So this would rewrite as negative integral e to the u du plus the integral of 1 dx is x. I'm going to worry about my plus c in a minute here. The integral of e to the u is e to the u. I have to convert back to x. U was negative x. And if I don't leave negative exponents, this would be negative 1 over e to the x plus c. So there would be my simplification of that integral. Now if this e to the x was if this 1 plus e to the x was in the denominator, this would end up being a nice little interesting natural log. So let's look at something similar to that, but not quite as exact. I want to put some different numbers in here. Let's look at the integral of, and we have to be really careful on this one, we have to keep track of my negative exponents and my negative coefficients. This just looks like a mess. I can't separate the denominator. I could separate the numerator, but I don't think that's going to help. I might be able to find and simplify, flip these, find common denominators. E to the x, yeah, I just don't think that's going to do much good. We might get some things to cancel, but I think we'd end up right back where we're at. So let's go ahead and look at some strategies here. I'm going to let u equal the denominator. So this might equal a nice little 1 over u to u if I can get it to work. So u is equal to the denominator. Du, the derivative of e to the x is e to the x. The derivative of e to the negative x is negative e to the negative x dx. That's my numerator. So if I think about this, this is 1 over u to u. Okay, because this entire expression is right up here. And the integral of 1 over u to u is natural log absolute value of u. And u in this case is e to the x plus e to the negative x plus c. So this would be my solution. Now you remember you can check it by taking the derivative. I'm just kind of curious on this one. You wouldn't have to simplify this, but I want to look at that. So this would be a common denominator of e to the x times e to the x. When you multiply like bases, you add exponents, e to the 2x plus 1 all over e to the x. And then this is a quotient. So this is log absolute value of e to the 2x plus 1 minus natural log of e to the x. I can pull this x out front. And then minus x. Yeah, this doesn't really do much good. So this would be another solution, but I think this one's just fine. You don't need to go through and simplify. I was just kind of curious to see if it worked. Now, last topic here, logarithmic differentiation. This is different than just taking the derivative of a log. We're taking the concept of simplification and putting things into a form where I can take the derivative. Now, this is something that can make things easier for you, and it's something that sometimes you have to use out of the fact that you have no other choice. So sometimes this is good for simplification to make taking derivatives easier, but sometimes it's required. So again, we can't say that we have to use it all the time, but sometimes it is required. And it's required when I have an expression that looks like a variable to a variable and I'm asked to differentiate it. Now the reason being is if I have a variable to a variable and I take the log, when I take the log I can pop that out front. So it's required in that case, helpful in other cases. So let's go ahead and look at an example where it's helpful but not required. And it's fun to do, so it can be a choice. I guess the third option is it's just fun. So required, helpful, and fun. So let's look at a case where we have a function like f of x equal, let's do x plus 3 to the 5th over 2x minus 1 to the 4th. This is a quotient rule with a chain rule on top and bottom. So I could definitely do this problem with the quotient rule and chain rules involved. So I could use the quotient and the chain rules. But I'm going to use logarithmic differentiation. Now the process of logarithmic differentiation is, first of all, replace f of x with y because they're interchangeable. That's our dependent variable. And then, because I want to get rid of these exponents and this quotient, I'll take the natural log of both sides. So when I take the natural log of both sides, I see right away this is the natural log of a quotient, which is the difference of the logs. And this is the whole idea of logarithmic differentiation, is to be able to rewrite. Now I have these exponents. I can pull those up front. 5 natural log of x plus 3 minus 4 natural log of 2x minus 1. Now I take the derivative of both sides. This is going to also involve the chain rule and implicit differentiation. The derivative of the natural log of y is 1 over y prime, or dy dx. I'm going to use dy dx here. And then the derivative of these, that's pretty straightforward. I drag the 5 along. The derivative of the natural log of x plus 3 is 1 over x plus 3 times the derivative of x plus 3, which is 1, minus 4 natural log. The derivative of the natural log of 2x minus 1, the derivative of 2x minus 1 is 2. So let's go ahead and simplify this. 1 over y dy dx. So I have 5 over x plus 3 minus, looks like we have 4 times 2 is 8. Oh, this log isn't there. Sorry about that. Because it's 1 over the argument times the derivative of the argument. So minus 8 over 2x plus 1. Okay, I could find a common denominator. This is not my answer yet. And don't drop the left-hand side. I have 5 times 2x plus 1 minus 8 times x plus 3 all over x plus 3 times 2x plus 1. Don't drop the left-hand side. It's really important with logarithmic differentiation. So I have 10x plus 5 minus 8x minus 24 all over the product, x plus 3 times 2x plus 1. So simplifying, again, don't drop the left-hand side here. It's really important not to. 10x minus 8x is 2x. 5 minus 24 would be a negative 19 all over the quotient, x plus 3 times 2x plus 1. Now, this is what we have to do to finish. I don't want to know what 1 over y dy dx is. I just want to know what dy dx is. So I have to multiply both sides through by y. Now the y's cancel on the left. On the left, I'm left with dy dx equal 2x minus 19 all over x plus 3, 2x plus 1, and then y. But I don't remember what y was. It was so long ago. X plus 3 to the 5th, 2x minus 1 to the 4th. Okay, and we can see that some things cancel. This x plus 3 cancels with here, leaving us with a 4th power, and then I can combine these. So I end up with dy dx equals 2x minus 19 times x plus 3 to the 4th all over 2x plus 1 to the 4th. Actually, to the 5th. And I think I copied this one wrong. I think it's a 2x plus 1. Yeah. I think I might have a mistake here. So when I rewrote this right here, this should have been a minus. So let me go through and fix that. Sorry about that. So if this is a minus, this would be 10x minus 5. So this would be minus 5 minus 24 would be a minus 29. So those are my simplifications here. And then this is supposed to be, let me double check, 2x minus 1. So this is a minus 1. And what clued me into the fact that I probably was wrong was these denominators were different. And these should probably end up being the same because I didn't really change them anywhere. So this would be 2x minus 1 to the 5th. Okay, so this is my derivative. Okay, so when you're working with logarithmic differentiation, this is my simplification of the derivative. This is as far as it simplifies. However, I could have just used the quotient rule as well. And if you want to run through the quotient rule option, you can. Now we said that it was either fun, helpful, or required. Well, that one was kind of fun and helpful. Let's look at an example where it's required. This is when we'd have a variable to a variable. So let's look at something like f of x equals, let's say, 2x to the natural log of 3x. Now here, let's be really clear on this. The x is my base, the 2 is just a coefficient that I drag along. Unless I put parentheses around it, then 2x is my entire base. So I'm going to leave 2x as my entire base. So derivative. So we'll replace y, and the reason I have to do this is I don't have a formula for something like this. I don't have a formula for a variable to a variable. So I have to pop this variable out front. So parentheses are important here. Next step, we take the natural log of both sides just like we did last time. Pop the natural log of 3x out front. And then I have natural log of 3x times the natural log of 2x. I'll take my derivative, 1 over y prime, or dy dx is my preferred notation here. And then I have a cute little product rule. I have my first and my second function. So I have my first times the derivative of the second, which is 1 over 2x times 2, plus the second times the derivative of the first, which is 1 over 3x times 3. Now this is a product rule, so there's no denominator. So I'm going to simplify this up a bit. And on the right hand side, it looks like I have the 2's cancel, so I'm left with the natural log of 3x over x. And again, the 2's canceled. Plus, the 3's cancel on this one, natural log of 2x over x. I have a common denominator, so I have 1 over y dy dx equals natural log of 3x plus the natural log of 2x all over x. Now we're going to go ahead and multiply through by y now so we can get our final solution. On the left hand side, the y's cancel. And on the right hand side, I just need to go ahead and plug in for y. Except I don't remember what it was so long ago. 2x to the ln of 3x. 2x to the ln of 3x times ln of 3x plus the ln of 2x. Please put parentheses around the arguments of your logs all over x. So this is my derivative. Now, there's nothing that cancels here. You might be tempted to cancel the x's, but remember this is x to an ln power, so there is nothing that cancels. So we've done quite a few things here. The only thing we haven't done is a trig, logarithmic differentiation, but again, if it's a variable to a variable, you just go through the same process, simplify as much as possible. And when you're working with these, be very careful. You saw how easy it was to make a mistake. I just changed a sign on one thing and it kind of messed up the whole problem. So again, be cautious and check all of your work. If you have questions, as usual, you're welcome to text me with any questions. We also have the Pearson Connect tutors that are helpful and available to you 24/7 as well. Good luck on this assignment.